Hey guys, we're continuing with the energy unit. Now we're moving on to worksheet 2. In worksheet 2, we're going to focus more on the bar charts and more specifically what the system is for an object. So here we have this example. We have this cart. It is on a spring, the first part, and then the second part, it is moving and it's at the top of this loop. So we have here what we call an LOL diagram. So LOL, why is it called that? Well, it looks like LOL, but the L's are bar charts. So you'll have like position A, position B. The circle is where you're gonna put your system down. So they tell you the system on this worksheet, but this is kind of like back when we did system schemas. It'd be the same kind of concept. Anything in our system is energy we need to track. So let me write this down. We have the cart in our system, we have the earth, we have the track, and we have the spring. So we'll show why we want this, but all right. This cart, it's right here, it's sitting on the spring. So the spring it's scrunched up, so we're gonna say there's elastic energy there. The cart is not moving, and since it's on the ground, there's no potential gravity to make it go faster. So I'm gonna say it's all EE. So that's all there is for position A. Now let's go to position B. The spring has been unwound, so the cart has left the spring. So the spring, there should be no elastic energy left. We're frictionless, so that means we have no E dis. So it looks like we have some combination of EK and EG. I'll just put 2 EK and 2 EG. The big thing is that if we're saying there's 4 boxes on the left, there should be 4 boxes on the right, because energy can't be created nor destroyed, only transformed. That's the law of conservation of energy. I'm going to make an equation based off this. And the way these equations work is the left side has to be equal to the right side. So EE is equal to EK plus EG. And that's all we need for this problem. So hopefully that feels good for y'all. I want us to go over one more real quick. So 1B, it's the same as 1A, except this time we have the cart, we have the earth, we have the track in our system, but not the spring. So very specifically, we do not have a spring in our system. What does that mean? It's almost like this section here, the spring, like this is all gone. And it might even be easier to see this, like if you could imagine this was just not there, not in existence. So this cart's just sitting there. It's not moving. There's no kinetic. There's no change in gravity yet, so no EG, and there's no spring, so no EE. Weird. Well, position B looks the same as before, and if it's the same as before, it'd be 2 and 2. All right, so what is happening here? I have this uneven equation. I have EK plus EG is equal to like no energy off the side here. What's happening is something outside of our system is giving me energy. Something outside's giving me energy. We're going to call that work. Now, work, I will define it over here. So if we go back to day 1 notes, I will place it over here. And let me go to my day 1 notes. So in day 1 notes, we see here, work, W, that's the symbol for W. Work is equal to force times displacement. So work is equal to force times displacement. Put this in your day 1 notes. And yeah, so what is this all about? Well, so work is a term in physics. When you see work, it correlates to energy. And when you think of someone working, I think you think of maybe like let's think of a construction worker or maybe like a mover. So these people are working. You might think of people having to sweat because they're actually putting in energy to move around. So all these are coming to mind for working. So that's energy. Fun fact about work, if you remember energy is scalar and work is energy, then work should also be scalar. So work is equal to force times displacement. Both of them are vectors. A vector times a vector gets you a scalar. So that might be interesting to note. If you are somehow getting energy into your system that's not being tracked properly, we call that work, and that's what happens in 1B. So, all right, I'm going to pause this. I want you to try 1C, 1D, and we'll come back together. We'll see how you do. So I'm going to pause the video. You work on 1C, 1D. Let's see what you get. All right, 1C was the exact same thing as before, except there's friction now. And I did this very specifically. So position A is the same, just elastic. We have the spring back in our system. But now, what's different is the cart is still at the same height. So I like to say there's 2 boxes of EG. Well, if there's 2 boxes of EG, then that means the remaining 2 boxes have to be split between EK and EDIS. I said there's 1 box of EK, 1 box of EDIS for this. Why I chose EG, it's a bit like, if I was grading your stuff, I probably wouldn't take off points for this so specifically without numbers. I think we're for sure at the same height as before. So what probably that means is that we are moving slower when we're at the top of this, and we lost that extra energy to EDIS. Unclear to know without the numbers, but the big thing as a grader at this point, what I'd be looking for, 4 boxes here, 4 boxes here, is all the energies accounted for. All right, let's go check 1D. So 1D, same scenarios last time, except as 1A, I should say, except we are not as high up. That means we have less potential energy gravity. That means that amount we lost there is an EK. It's frictionless because problem 1A was frictionless. So hopefully y'all felt good about that. All right, let's look at problem 2 here. I think I'll say this: you guys should try to do problem 2. Let's see what you end up getting, and I'll explain my process. All right, 2A, most people get this. As long as you're kind of looking at what's going on here, your height is 0, your EG has to be 0. If your velocity is 0, your EK has to be 0. So it's really just EK of position A is equal to EG of position B. I think most people get that. Let's look at 2B though. So 2B, same thing, but this time we have friction. Our system is still car, road, earth. All right, so let's just say it's the same scenario as last time, right? We have EK, we have EG, but we also have EDIS. Now, some people, when they do this, they say, okay, 4 boxes, I'm gonna go 3 and then 1, which, if I'm grading this, I probably wouldn't be as much of a stickler about it. You know, it's technically right between the two, but if I'm saying that, you know, this height difference was 4 boxes here, if I want to say the same thing, and this is 4 boxes, and I have a box over here, what does that mean? That means I probably need an extra box over here. So you can add like that 5th box there to be more specific. You don't have to add that 5th box. Like, as long as both of these sides are the same amount of boxes, that's what's most important, but just something to think about. All right, let's see how y'all do on 3A and 3B. I'm actually going to walk through this one by one with y'all so that we can help each other out. So the system here is car, road, and earth. There's this person here. H is 0, V is 0. So we have no EK, no EG, there's no spring, no EE. But we're going to end up with what looks like a lot of height, and it's not moving, so no EK, no EE again, and no friction, so no EDIS. All right, so we're going to end with all EG. Well, it just kind of looks like my car has gone from 0 energy to a lot of energy. So that means work must have been added to the system. This work from the person must have been added in. So remember, work is the one way you can have uneven boxes in your bar diagrams. Now, good job if you got that. Let's look at 3B. 3B is a little different here. So 3B, we have the same thing, except our system is car, road, earth, person. It's the exact same scenarios, just this time we're including the person in here. So position B should be the same, but how do we include the person? Now, some people might try to get tricky. There's still no EK, no EG, but hey, maybe a person's elastic, maybe there's something like that. Without getting too cute about it, I think we should just call it energy from the person, or sometimes you could call it other energy. So basically, energy we're going to count. Other energy is equal to EG. Now, a lot of my students get mad at me. They're like, that's a trick question, whatever. There's not a lot of other energy opportunities for me to show you in this class. So I'm showing you here. You probably won't have a question like that on the test, but I just want to show you. persons in our system, we have to track that energy, so that's where it shows up. So this is what I have for 3B. All right, let's I'm gonna do all of problem 4 real quick. You guys should try it first, and let's compare and let's see if we get it close. This is my answer for 4A. I'll let you check that, and then I'm about to do 4B. So if you're having to change things, go change it. I'm going to do 4B in a second. This is what I got for 4B. Hopefully you're still feeling good. And now I'm going to do 4C, which is a repeat of 4A, except we don't include the spring. All right, and this is what I got for 4C. So the spring energy became work, and that's equal to EK plus EG. There's no friction because it's 4A. So yeah, there we go. All right, I'm going to do the same thing for 5A. I'll do 5A first, but you guys should try this out on your own, and then I'm going to show you my answer. All right, 5A, pretty standard problem. Everything's in the system. EE becomes a combination of EK plus EG. We're higher up, so we have more EG. We're also moving. There's some EK. I'm going to do 5B now. So 5B, I decided, hey, I'm going to be kind of tricky here. I'm going to put in 5 boxes, Whatever it is, you don't have anything to equal on this side anyway, so it's fine however many boxes you want to represent. In this scenario, if we know that this is work like elastic, work caused by the spring, then this is greater than this one. But, all right, let's go to 6A, 6B. This will be the last one for this video, so I'll work this all out with everyone. So we have this system, we have the jumper, the earth, the cord. If you want to go ahead and do this on your own, go ahead. You can really test yourself. So position A, the person's just standing here. Now your bungee cord is not activated yet. So there's no elastic energy. It's not like stretching out, it's just kind of folded over on itself. We have all this height and we're not moving. The person jumps off, the bungee cord catches him, we're at a point where we're not moving, we have some height, let's call it, maybe 1 box, and then that means the rest is the bungee cord. Now what's interesting is, let me write this all out, we have this EG from before, EGA, and we have EGB over here just so we can tell them apart. They're different heights. EGA is greater than EGB. All the other scenarios we've done, we basically always went back to height 0. But in this case, if you don't use up all the height, you still have some potential energy left over. So that's interesting. Let's do this last one. We take the bungee cord out of our system. What will that do for us? So it'll start off the same, EGA, EGB, but all the remaining boxes that aren't adding up, we'll call that work. All right, that's it for this video. Thank you guys. We'll move on to some more worksheets after this.